Hi, I'm John Saffell. I'm CTO at Alphasesne, and we're going to talk today about analyzing our air quality data. The first thing I'm going to say is that we all use R squared. How many times have you seen an R squared plot between 0 and 1, and purely by those two digits, whether it's 0.89 or 0.33, makes you decide whether the data is any good? The first thing to remember is sometimes R squared is an uppercase R and sometimes it's lowercase. And those depend on whether your data of the two axes are independent or they correlate. And with a capital R squared, it's multiple correlation, and with small r squared, it's not correlated. It's quite important. And almost all variables in air quality are interdependent. For example, relative humidity will affect both your sensor being tested as well as your reference system. Let's now have a look at how we can make our data look better and how some people make their data look worse. Okay, making your data look better, trick number one. Compare on the X and Y axes equivalent sampling systems. Here, for example, is data of electrochemical NO2 sensors, and they are both effectively the same sensor technology, measuring co-located in the same time in the same location, and guess what? You get incredibly good R squared of 0.95. That shows that the sensors are repeatable with each other. It doesn't show the true quality of the data relative to a reference system. What's the next trick? The very important trick is if you're going to measure data, measure it over a wide range of concentrations. This allows you, in the way that R squared is calculated, because of the effect that you divide by the variance, to give you better R squared. So if you're measuring a lot of low concentrations, make sure that you measure some high concentrations so that you have an R squared plot that is extended beyond the low range. This alone will improve your R squared. Secondly, important issue is that most sensors operating at really low concentration ranges, we're talking about low parts per billion of gas concentrations and under 5 micrograms per cubic meter of air quality particle densities. When you're looking at these low levels, you start to approach the signal to noise level of your sensors and your sensor electronics. And when you're working down there, you'll get higher errors just because you're working near the LOD. Third trick of making your data look good is don't try for a unity slope on your two parameters. Allow to fit both the intercept and the gain to optimize the difference in locating the two sensors. When you do that, you're then removing all the bias errors and you're only looking at the random errors. This, for example, shows data that on the left has not been normalized for the bias errors, and on the right, after normalization, it has. An important issue that is that many air quality networks that are set up automatically adjust both the offset and the gain when calibrating, and you don't have a knowledge that this has happened. So be aware of whether you're allowing the R squared to represent a unity gain or a non-unity gain. The next thing that you can do is compare two different technologies. This is especially a problem with particles. For example, when measuring with low-cost particle monitors, you're measuring the integrated scatter by what is called nephelometry. Other technologies include single optical particle counting, beta attenuation, gravimetric, and resonant TOM measurements. All of these are different technologies that measure different properties of the particles. And so when you plot them to try to get an R squared, you have to be aware that you're actually measuring two different parameters and trying to get an R squared value. And this is sometimes a source of an error. For example, we show here an electrometer measuring ultrafine particles versus a microethylometer, which measures optically black carbon. This next slide shows another problem of the period of measurement. Reference stations will average over a fixed period of 30 minutes, 15 minutes, 60, maybe even 24 hours, and will give you a single reading. whereas low-cost air quality networks frequently give out readings as fast as every 15 seconds or 1 minute. If you don't average those data correctly, or if you try to compare data averaged at the end of the hour with data during an hour, you will get a phase shift in your data, which is very hard to correct. These two graphs show how if you don't accommodate correctly for the average time period in your reference and in your sample system, that you can easily get a phase shift, which would mean that your error analysis in terms of an R-squared would be unreasonable. Let us now look at something that is very recent. This data is collected by Rod Jones in the Breathe London campaign between December 2019 and July 2020. And the red line represents March 23rd, which is the day that the UK was locked down. You'll see that on the earlier period, the gas concentrations are generally higher than after lockdown, as we'd expect. That's interesting. However, what we're interested in is how the same sensor system in the same location using the same analysis produces different results. We first of all take the two segments and separate them at March 23rd into Group A and Group B. And we can separate them easily, and we'll add some normal distributed Gaussian distribution noise, and that is equivalent to representing what happens at the limit of detection, which for these sensors is about 2 to 3 parts per billion. So we're adding in noise and seeing how that affects R-squared and the alternative method of calculating error, the root mean squared error, RMSE. And here in this table we can see that for both A and B, as we increase the distribution of our noise from 1 sigma out to 3 sigmas, which is used for the limit of detection calculations, and 10 sigma, which is used for the limit of quantification, LOQ, we can see that the R-squared rapidly deteriorates as we increase the noise. And it also heavily depends on whether we are measuring noise over a high dynamic range or a low dynamic range. A has a high dynamic range, B has a low dynamic range. And you'll see that where, for example, we can get a 0.85 for the noise for the R-squared before lockdown, it deteriorates to 0.49, although it is the same system, the same sensors, the same location, showing that R-squared can misrepresent, and you'll note that the RMSE remains unaffected by the range of the data. Hence, recommending RMSE as a way of data analysis. We've looked at the problems of R-squared, we've looked at RMSE, and we haven't even considered that when you're in the field, the time of the year is important. Both seasonal and climatic variations are critical. The patterns of temperature and humidity are very different for different places on this planet and for different seasons. Winter and summer are quite stable. Autumn and spring are quite dynamic in terms of temperature and humidity transients. The average temperature is clearly different between winter and summer as well. Hagen and Cross showed that when they calibrated their sensors during one season, when they then tried to apply those calibration coefficients into another season, although the R-squared remained the same, the data quality changed. Furthermore, temperature and humidity rapid transients can cause problems in sensors, and you must be aware that different manufacturers of low-cost air quality networks do different tricks. Some of them will smooth it, some of them will try to analyze it and correct it, and others will simply cut out transient data. Just know what you're dealing with. In conclusion, R-squared is easy to use. Are you actually nulling both the offset and the gain, or taking them as a zero offset and a unity gain when you're calculating R-squared? Next is, when you're comparing different technologies, remember you often are comparing different measurements fundamentally. The R-squared is very susceptible to the range of measurement, and don't forget that you've got to be averaging over the same period as your reference system, or you're being unfair to yourself. And finally, our take-home message, RMSE is preferred measurement over R squared. Thank you for your attention, and just a couple of pictures of cities before and after lockdown. Thank you very much.